I will also pass the floor now to Geert DEGRANDE from Catholic University of Leuven. Geert is a specialist in ground-borne vibration and structural dynamics, and he's also a friend and a colleague from the IWRN. So you can see that you have an IWRN gang here. And without waiting more, Geert, the floor is yours.
Okay, thank you, Pierre-Etienne. So the title of this of my presentation will be on prediction models for railway-induced vibration in the built environment. Next, please. So the next slide, in fact, points out that we have many challenges to cope with when doing predictions, since we're dealing with coupled problems, both at the source, that could be a track at grade or track in tunnel, as well as at the building site where potentially vibration and noise are experienced. Vibration is propagating through layered soils. We have to deal with moving quasi-static as well as dynamic axle loads, and to take into account multiple excitation mechanisms such as wheel and rail unevenness, rail joints, and parametric excitation. And this needs to be done in a much wider frequency range than we're used to do, for example, in earthquake engineering, since we cover the frequencies up to 80 Hertz and potentially up to 250 Hertz for noise. In practice, there is a general need for detailed vibration analysis, but also for scoping models that are quick to run in early design phase. And what we see happening also in practice is that there is a need to do parametric studies to deal with uncertainty, to design inexpensive, well, we see that mitigation measures could be expensive, so there is a general need to optimize them. So in my talk, I will take the opportunity to explain where we are with respect to numerical modeling, and also take the opportunity to link up with empirical models that are frequently used in practice, as to end up with a proposal to develop hybrid models as we aim to do in the Silverstar project. Next slide, please. So in order to illustrate the state of the art on modeling, I will make use of a case history where a couple of years ago in Leuven, we did extensive measurements along a conventional ballast track on embankment, which is close to a building you can see on the right top, which is an administrative building with a repetitive structure in reinforced concrete and infill masonry. And that building is located at about 30 meters from that railway track that is operated by commuter trains as well as freight trains. Next slide, please. We set up a very extensive measurement campaign where we had accelerometers attached to the sleepers, to 10 sleepers, also to the rails. We put strain gauges on the rail web. In the free field, on 3 parallel measurement lines, we installed 18 seismic accelerometers. And on the 4 stories of the building, we had 4 triaxial wireless Geo6 sensors. And measurements were performed in 2 ways. So we recorded train passages over 1 week, day and night, both commuter and freight trains. And second, we measured transfer functions from track to free field into the building using multiple excitation points along the track. Next slide, please. A very important information we need are dynamic soil properties, as you all are aware of. So we set up an in situ geophysical prospection campaign using spectral analysis of surface waves, seismic refraction, and seismic cone penetration testing. And you can see the maximum a posteriori probability soil profiles in thick blue line on the tree grass below, which show from left to right the shear wave velocity as a function of depth, the material damping ratio, and the P wave velocity. What you can see is that we have a relatively good estimation of the shear wave velocity between, let's say, 1 meter depth and 15 meter depth. Below that depth, the resolution of our SASW test was not sufficient, And for very shallow depth, we only can rely on the SCPT tests. The gray lines on the curve all show possible realizations of soil profiles that would meet the measurements we have performed. So what you can see on the left is that indeed the uncertainty is very high or becomes higher at depths larger than 15 meters. And so is the case with our knowledge about the material damping ratio in the soil, where we have good estimates up to a depth of about 7 meters, and where we see the usual profile with decreasing material damping ratio with depth. However, below a depth of 7 meters, the uncertainty raises substantially. And a similar conclusion can be drawn with respect to the P-wave velocity, which is shown on the right. However, there the uncertainty on depths lower than 7 meters is not so high, as we know that the groundwater table is present there. So a good estimate of the P-wave velocity would be in the order of 1600 meters per second. But this already points out that in this type of prediction models, we will have to cope with uncertainty. Next, please. A similar remark can be made with respect to the building. So we made a finite element model of that 3-story building. It was coupled to the soil, and we set up a separate measurement campaign using ambient excitation, so due to wind loading, to identify the global modes of the building. And you see them depicted in gray. Together with the red numbers, these are the experimental results. The finite element model was updated, taking into consideration over 15 building parameters. And you see that finally we find a quite good correspondence between 2 lateral modes and 1 torsional mode that are shown here, together with the estimated damping ratios of these modes. Apart from this, we did separate testing of on the different floors of the building using, again, ambient excitation, but also forced hammer excitation in order to identify the modes of the building, of the floor. We see that floor modes are coupled between stories, and we were able to identify with reasonably good accuracy the modes of the building up to, let's say, 25 Hertz. But still, there is some uncertainty in the building modeling involved. Next, please. When it now comes to making prediction, what is usually done today is to make computations in 2 steps, where it is assumed that the dynamic axle loads on a track or in a tunnel track will not so much be influenced by the proximity of nearby buildings. So a 2-step scheme is set up, where in a first step, the free field response is evaluated. So we would call that the incident wave field. And this in turn is also done in 2 steps. So first, a track soil interaction problem is solved to compute the dynamic axle loads, as I will show next. And subsequently, the dynamic axle loads are applied to the track to obtain free field response. In a next step, so in the final step, that incident wave field would be applied to a building, as you can see on the top right, where you see the finite element model we used for that building, which is coupled to the soil by means of a boundary element model of the foundation and the subsoil layers. This is done in a next step and is quite, well, similar as we usually do in earthquake engineering. Next, please. So first, the transfer functions from track to free field. We use several models first to identify, to calibrate the properties of the ballast, the embankment, and the topsoil layer. We did not solve an optimization problem, as the models we are running are a bit too expensive to be used in an iterative scheme. And this is certainly an aspect that could be addressed in the future. In order to compute the transfer functions between track and free field, we use a model that, well, is depicted in the middle, where we in fact model a cross section with finite elements and boundary elements. So the mesh is 2D. However, the computation is 3-dimensional, since we take into account the different waves that can propagate in the direction of the horizontal plane. I won't go into the mathematical detail, but this is a convenient way to compute waves radiated from railway tracks and to compute transfer functions. And we have a suite of tools available, which are called Traffic, Bamfen, and Wavefem, to accomplish this task. At the bottom, you see results of predicted transfer functions between track and free field on the central measurement line we install between the track and the building. So these are the receivers B1, B2, and B3. The black solid line shows the prediction using the average estimated soil profile. The gray shaded area shows the 90% confidence interval on our prediction using 20 of the possible identified soil profiles. So they show already an indication of the uncertainty we have on our model prediction in terms of transfer function. And we see typically that uncertainty raises with frequency and also with distance to the track. The light shaded gray line on the graph is the average measurement result of our transfer function. And we see that sometimes that result is outside the bounds of our prediction, which means that there is still some model and parameter uncertainty involved in our prediction. Next, please. In a subsequent step, so now that we have transfer functions, we also need to compute the axle loads. This is typically done by using the compliance of the track, the compliance of the vehicle, and using as input the unevenness of the track. So in this particular case, we made a vehicle model of this Siemens D0 train by using a multi-mass rigid body model, as you see on the right. Infrabel could give us power spectral densities of unevenness measured on this track. And using these, so using the information we have on the track as well as the vehicle and the unevenness, we can make predictions of time histories and frequency spectra of these dynamic axle loads, as you see on the bottom figure. Next, please. So with this information, so with the transfer functions available, as well as the dynamic axle loads estimations, we can make prediction of free field response. And I again show these on the central measurement line between track and building at the distances B1, B2, and B3. So B1 is next to the track and B3 is next to the building. On top, you see the comparison in black of the predicted response using the map soil profile, while in gray line, you see the measured response. And you see that, well, in amplitudes, we're not far away. On the bottom slides, I show similar results, but now presented as 1/3 octave band spectra. Please mind that the vertical scales all cover 60 dB. However, the ranges are different. So the first graph is from 20 to 81. The second is from 10 to 70. Again, the black line shows the prediction of the free field response during the passage of a train using the average estimated soil profile. The gray light line shows the measurement results. And then we made alternative predictions taking several soil profiles that were, well, equally valid, let's say. So soil profile 1 would be a bit softer. Soil profile 6 in red would be a bit more stiff. And we see that this uncertainty on the soil properties results in some deviation in prediction on the vibration levels. On average, I would say we do a relatively good job with an error estimate in the order of 6 to 10 dB, as you can see on the bottom graphs, except in the very low frequencies where the discrepancies are higher. And this most probably is due to our incomplete knowledge of the properties of deeper soil layers. Next, please. So we continued that exercise to make prediction in the building for a train passage. And on the right, you see here our prediction in the basement, on the ground floor, first floor, and second floor of the buildings. That's from A to D with the similar color codes as on the previous scales. And we come to similar conclusions that despite all efforts we have taken to determine track unevenness, vehicle properties, soil properties, and building properties, the prediction is relatively good from frequencies, let's say, from 8 to 16 hertz, except in the very low frequencies. Now, this idea, this makes us concluding that we can do a relatively good prediction. However, the effort needed to determine parameters is substantial. And so we believe, next, that we can find inspiration, next slide please, in procedures that are often used in practice, like proposed in the ISO 14837 or in the FRA procedures, where the vibration level, as you can see on the bottom, is predicted as the superposition of a force density, a line transfer mobility, and a correction term from the building. Next, please. So that line transfer mobility would be determined by making a superposition of different point source transfer mobilities. The force density would be computed indirectly by making the difference between a vibration velocity level and a line transfer mobility. And the receiver term would be a correction term taking into consideration soil structure interaction, attenuation over the height of the building, and floor resonance frequencies. Next, please. So what we believe is that if we look at the pros and cons of the numerical models and the empirical models, we could try to find a way to use best of both worlds. So to combine the flexibility of numerical models to account for a wide range of parameters with the advantage of empirical models as they are able to account for local terrain, track, and soil properties. And to come up with a hybrid model that, for example, could be used when new railways are constructed in proximity of existing buildings, where you could use numerical prediction of force density combined with experimental values of line transfer mobilities and building response measured on site, or vice versa when you construct new buildings in proximity of existing railways. Next, please. This is exactly what we aim to do in the Silverstar project. So within the frame of this project, which runs since November 2020 over a period of 2 years, and which is supported by Shift to Rail, we will develop such a hybrid prediction model together with Vibratech, who is the project manager, Wolfville, Southampton University, EMPA, and Unife, and this in close collaboration with Fine2. Next, please. So the aims of that project will be to develop such a hybrid methodology that would enable transposition of vibration emission data from one situation to another, making the distinction between source, propagation, and receiver, to also define and validate a track-independent vehicle indicator, and to implement this methodology in a user-friendly software that would be equipped with a graphical user interface and will also interface with geographical information systems. Next, please. Well, we have been thinking about different possibilities to combine numerical prediction with experimental data. I have no time to go into this detail right now, so I will skip to the next slide, please. And next, please. Yes, thank you. And say that the collaboration is set up between KU Leuven and ISVR to use the available numerical methods to compute soil impedance and track soil transfer functions. This will be coupled into a hybrid prediction model that is inspired by the Ground-fit model available from Vibratech. And we will aim to provide a model that is fast to run on PCs and that combines the advantages of both worlds. That will be made compatible with international standards and guidelines and linked up with Wolfville's IMI geographical information system as to visualize the response. Next, please. So in summary, I can say that great advancements have been done at many universities to come up with numerical prediction models. They are needed to perform parametric studies in a next step for robust design optimization, and very importantly, to do forward stochastic modeling as to account for the many uncertainties we have to deal with. And the outlook is that we further develop those models, those detailed models, but at the same time ensure that industry can use efficient models that are fast to run and take advantage of the accomplishments of those numerical developments as well as experimental results that are available. Thank you very much.
Thank you, Geert, for this impressive tour into modeling, and also the how you can come to some industrial products and software with the cooperation of partners. And I think this is what something which is quite interesting to note, that nowadays we really need some cooperation between universities, engineering companies, and railway companies in order to come to feasible results, even in terms of modeling and understanding phenomena. But that's not new at the end of the day.